Okay, so before you watch the video, if you have a way of printing the handout for section 1.2, you may want to do that. So in section 1.2, we're getting a sense of what variables are used for. So we use letters to stand for numbers, but I want you to get a sense of why we do that. So let's take a look at question number 1 on this handout. So this company, Net Movies, charges a monthly fee of $13 plus $2 per movie. Okay, I meant for that to be capital. Okay, and then I'm asking you to think about what the monthly cost would be for all these various numbers of movies you might rent in a month. So why don't you pause the video and try that, and then let's check if you were thinking about that correctly. So if you rented just one movie in a month, the monthly cost would be $13 plus $2 for the movie, so it turned out to be $15. But if in a month you rented 2 movies, you'd still have to pay that flat fee of $13, but now you'd have to pay $4 because you rented 2 movies, and so now your monthly cost would be $17, wouldn't it? Okay, so if you rented 3 movies, it would be $19, wouldn't it? Because you rented 1 more movie, so that would be $2 more. See, that flat fee of $13, you're just going to pay once, and then you're going to pay for $2 for each of the movies you rent. So if you rented 3 movies, okay, you're paying $2 for each of them. Okay, then that's going to turn out to equal, let me write that separately. So $2 times the number of movies, 3 movies, so that would be the 19 that we expected. Okay. Now, if you rented 5 movies, I couldn't just add $2 to 19 to get the correct amount, because you rented 2 more movies here. See, this would be 2 more, okay? Not just adding 1 movie. So we would have to add 4 to that. Our answer should be 23. See, that flat fee of 13, $2 for each of those 5 movies, that would turn out to be $23. And then wouldn't we do the same for 10 movies? If I rented 10 movies, $13, $2 times 10 movies, that would wind up being 13 plus 20, or $33. And then finally, if I rented 12 movies, that should turn out to be $4 more, because I rented 2 more movies. That turns out to be 37 movies. Okay. Now, what I would have asked you to do in class is to let a letter like M stand for the number of movies. Okay, so if I let M stand for some number of movies, then I could represent what the monthly cost would be. And I could do that by thinking about how I calculated these monthly costs over here. Every time, didn't we have to pay $13? Every time, didn't we have to pay $2 for each movie? And it's just that M is standing for the number of movies that we wound up renting. Now, when you have a number in a letter like that 2 times M, when you're multiplying and you have a number in a letter, that's what 2M means. When you don't put something in between, then it's assumed to be multiplication. So this expression right here kind of generalizes what's going on here, so that you could use that expression to calculate what the cost would be. So if somebody came in and they rented 15 movies, then I could just put 15 right here. I wouldn't have to think about the context. I could just do 13 plus 2 times 15, 13 plus 30 to get my answer. I wouldn't have to think through the words of the problem to get there. But see, that 13 plus 2M, that M just stood for how many movies. And so if I know the monthly fee is 13 plus $2 per movie, then it's kind of like I'm translating almost the words. You know, $2 times the number of movies would be 2M. Add that to the flat fee of 13. So we're going to start seeing some letters. Here's where sometimes students really fall apart. So you really have to try to understand what these letters are intended to do. They're supposed to stand for some quantity, right, in real life. But in elementary and intermediate algebra, a lot of times you don't know the real context. So you don't know what those letters represent. Okay? So like on question number 2, we're being asked to evaluate some expression. We don't know what the context is. It just says evaluate 100 minus P, and it tells us that P is 4 and Q is 3/4. So that said P, so in place of the P, I'm going to put a 4, I'm going to work it out, and I'm going to get 96, right? We don't know the context. It could have been how much change you would get for a $100 bill if you bought something that was $4. You would get $96 in change. We don't know the context. We're just evaluating the expression. Okay? Now on part B, P and Q have nothing in between them. When letters are written like that, or when you have like a number in a letter with no operation sign in between it, it means multiplying. So this means P times Q. P is 4, Q is 3/4. Now you have to go back to your 1.1 work. 4 times 3/4 is the same as 4 over 1 times 3/4. And then I can simplify first by dividing both 4 by 4 in both the top and the bottom, and what I get is the answer turns out to be just 3. Okay. Now another thing in section 1-2 is getting a feel for numbers and where they occur on a number line, and you'll start seeing some numbers that have a negative in front of them. So you'll start dealing with positives and negatives in this section. So typically, what I want you to think about is how I could draw this number line, and I could mark some key numbers, 0, 1, 2, 3, 4, and 5. Those are positive numbers. Typically, you write those to the right, and it would just keep going towards positive infinity. And then over to the left, that's going towards negative, negative 1, negative 2, negative 3, on down. So if I wanted to plot to show somebody where the number negative 3 would be on this real number line, then I would just put a dot right there at negative 3, okay? But you won't just have nice numbers like that. That, by the way, later you'll learn that's an integer. Okay? You won't always have nice numbers like that fall right at a tick mark you've already made. So if I were trying to do 3/2, I'd want to think about it either as a mixed number, so change it to a mixed number, it'd be 1.5, or think about it as the decimal, that would be the same as 1.5. So it'd be positive, so it's to the right, halfway between 1 and 2. That right there would be 1.5 or 3/2, depending upon how you represented it. Okay. Now negative 4.7. Negative 4 means you'd be all the way to the left 4 units, and then you keep going. See, this right here keeps going in the negative direction even more. 0.7 is like I'm thinking about this. I would have to think about this broken into 10 equal pieces, which I can't do. So kind of think about if you're halfway, that would be negative 4.5, then think 4.6, 4.7. So on your way to negative 5, maybe about right there, would be negative 4.7. Now for 16/5, it's kind of like B. I would need to know the decimal or mixed number form of that to be able to figure out where to put it. So I'm going to divide 16 by 5. 5 goes into 16 3 whole times with 1 left. So it's the same as 3 1/5. So that means I would go to 3, and then I need to be 1/5 of the way to the next number. So it's like I'd split up this into 5 equal pieces. Okay, that one I can actually draw. And then I need to be 3 1/5. So right there would be 3 1/5. Okay, that would be the same as 16/5. That would be the same as me cutting each of these into 5 pieces, right? Each of these into 5 pieces, and then counting, 5, 10, 15, 16 fifths. Okay, so you're going to have some questions where you might see a dot already on the number line, and your job is to name it, to give a name to it, and then you'll have some problems where you're actually going to plot numbers on a number line. All right, so let me do one example people always have trouble with. Okay, what if they gave you one and it looked like this? It was right there, okay? They will show the little broken up pieces. If you had to name that number right there, you could call it 1, 2, and then you'd have to name the fact that it's also 2/3 of the way, right? This is broken into 3 equal pieces, 3 pieces here. And it's on the second one. So that spot right there would be 2 2/3, okay? All right, so that's one way you could name it. All right, let me do another one of those. I'm going to do it down here. Okay, what if I saw that they had marked this spot, and they wanted me to name that. Okay, and then I would say that's 1 whole, and then I would count that it's broken into 1, 2, 3, 4 pieces this time. So that means each of these little pieces is a fourth. So this would be 1 1/4, that would be 1 2/4, that would be 1 3/4. So this spot right here would be 1 3/4. Okay, these problems right here, these types are the ones that people typically ask me about the most. So what you want to do is count how many pieces a unit is broken into. So count the fact that that's broken into 4 pieces, and then you can think through it a little bit better. All right, another thing is just looking at the relative sizes of 2 numbers. So when you have an inequality sign, the is less than or is greater than, those really come from an equal sign. See how with an equal sign you have the same space on either side? So that means whatever you have here has to equal what the right-hand side is, right? Because there's the same space on either side. Well, the less than symbol is formed by taking that equal sign and making it have less space on this side and more space here. Okay, so for instance, smaller number would have to be on that side, larger number would have to be there. Okay, and for a greater than symbol, it's the other way around. It looks like that. They kind of took the equal sign and made it have less space on here and more space there. Okay, so it's like 5 is greater than 3 is how it would have to go. All right, now, when you're trying to put an inequality sign in between 2 numbers, think about the number line. Think about how you got 0, 1, 2, 3, 4, 5 on up, bigger and bigger, and then this way it's 0, then -1, -2, -3, -4 on down. So think about where they are on the number line. Further to the left is the smaller. Further to the right is the larger number. Okay? Make it point to the smaller number. So wouldn't -11 be further to the left than 20? So -11 is less than 20. -11 is less than 20. Make the inequality symbol point to the smaller number. Okay, -3 and -6, they're kind of tricky because 6 is bigger than 3. But when you look at the number line, let me change the color to green. Here was -3, right? Isn't -6 going to be out here even further to the left? There would be -6. It needs to point to the smaller number. -3 is greater than -6. All right, 0 and negative 9. Negative 9 is further to the left, so I need it to point to negative 9. 0 is greater than negative 9. Negative 1.8, I would go negative 1 and most of the way to negative 2. And then negative 6.2 would be way out here, further to the left. So negative 6.2 is smaller, so I'm going to have it point to the smaller number. All right. Now, with 5, 6, and 7, we're going to be working on opposites versus absolute value. They're teaching you this because we're pretty soon going to get into adding and subtracting positive and negative numbers, and some of the rules use that language about absolute value. So taking the opposite of a number just means what would be the opposite of 5 would be what number would be on the opposite side of 0 from there. So see how that would be negative 5. So your answer would be negative 5. Okay, if currently you're sitting over to the left here at negative 12/13, the opposite of that would be the number that's the same distance from 0 but on the right. Okay, in this case, so it would be 12/13. So it's just literally changing the sign. Okay, and they can ask it in words like they did on 5. Find the opposite of the number. But that's kind of what these symbols mean here. When they, on 6, when they do that, they want the opposite of 0.46. That would equal negative 0.46. Okay. Here they want the opposite of negative 13/5. Okay, so this is opposite of this negative number. So that would equal positive 13/5. Okay, so your answer would be positive 13/5. So this would be the opposite of, and then the opposite of this negative number. Okay. All right, and then absolute value is different. Absolute value and opposites are different. Absolute value is distance from 0. Distance from the center. So it's always positive. Right? And the symbol for absolute value would be these two vertical lines like that. They're asking for the absolute value of 4. That would be 4. It's 4 units from 0. The absolute value of negative 1/2 is how far from 0 is negative 1/2? Well, it's half a unit from 0. Negative 6.2, the absolute value of that would be positive 6.2. 0 is 0 units from 0. Right? All right, and then notice here what they're asking for is the opposite of the absolute value of negative 4. So opposite, and then absolute value of negative 4. So you're going to do the absolute value of negative 4. Distance from 0, that would be 4. Then you're going to take its opposite, which would be negative 4. We're going to talk in section 1.3 a little more about order of operations and being careful how you interpret a problem. So on that one, you needed to do the absolute value of negative 4 before you could take its opposite. All right, and then another thing they get at in section 1.2 has to do with different types of numbers. Okay, and so I just wanted to give you a little chart that helps you, I hope helps you to see how these sets of numbers fit together. Natural numbers are really nice, like 1, 2, 3 on up. Doesn't include a 0, doesn't include any in-between numbers. That's it. 1, 2, 3 on up. Now, do you see how this box for whole numbers contains the natural numbers? So all of these numbers are part of the set of whole numbers. Really, they shouldn't write those there because they're already here. So 0 would be that extra number, okay? that you include, and 0 together with 1, 2, 3, 4, 5, 6 would be whole numbers. Now, for integers, they're also pretty nice, but they include all of the numbers so far. So they include the 0, 1, the 0, the 1, the 2, the 3, but then they also include -1, -2, -3, but not the in-betweens. So not -1.5 or anything like that, just those really nice numbers. 1, 2, 3 on up, 0, and -1, -2, -3 on down, okay? All right, now, rational numbers include numbers like fractions like 3/4. They can be improper, they can be negative like 22/5. They can be written as a mixed number like -3 and 1/7. They can be written as a decimal like 12.391. All of those would be rational numbers. Rational numbers are numbers that can be written like a fraction if we wanted to, where A and B are both integers. So if it's possible to write it as a fraction where A and B are both integers, then that makes it rational. But they don't have to look that way to start with. Repeating decimals, like 0.1 with that bar means 0.1111. That's actually the same. That actually equals 1/9. That's why it's over on the rational side, okay? And sometimes you have things like, more than one digit, like 3.25 with the bar would mean 3.2525, ... Still rational. That would be 3 and 25/99, and I could rewrite that as an improper fraction. All right, the thing is that in order to complete the set of real numbers, like when we were using that number line before, we usually use the integers to mark the units, the spacing, okay, so that we can plot numbers. But if we wanted to be able to name any number on this real number line, any number you pick anywhere, we would need both rational and irrational numbers. Irrational numbers are a little weird. They're like pi. Okay, pi is really approximately 3.14, but in reality, it's a decimal that would go on forever and never terminate, and it would not have a block of digits that's getting repeated. Same with square root of 2. If you did square root of 2 on your calculator, I think it's like 1.41, approximately, okay? Now, some radicals are on the rational number side, like square root of 16, for instance, is really 4, so it would turn out to actually be a counting number, okay? Or if I did the square root of 25/9, that would be over on the rational side because that would simplify to be 5/3. But a lot of square roots don't simplify like that, like square root of 2, square root of 7, those kinds of numbers would be over here, okay? E is another irrational number. It's about 2.72, a little less than 3. You'll see those, like pi, you've already had to use anytime you dealt with like area of, or in geometry, anytime you're dealing with a circle, you typically have pi involved. All right, one other one, you could have a number, something like this, like 2.101001001 ... That's a decimal that doesn't terminate and that doesn't repeat. It has a pattern, so I can do the ... but it's not a block of digits being repeated. So it takes both the rational and the irrational to fill up the real number line completely, to name any number you could put on that number line. All right, so there are some problems that ask you to indicate what set a number belongs in, okay, or to identify the natural numbers or the integers. So I want to think about this a little bit. So 5 is a counting number, so it is natural. But what this diagram tells you is that if you're here, then you're within the whole numbers, you're within the integers, you're within the rational numbers, you're a real number. So if you're a natural number, then you're also whole, you're also an integer, you're also rational, and you're also real. You're just not irrational. All right, negative 47 thirds, okay? So that one doesn't simplify to be very nice, right? It would be like, what is it, like 12 and a little something. So it's not a natural number. It's not a whole number, because those are really nice. It has a negative, but it's not an integer, because that's really negative. What is it really? That's negative 1, 5 and 2/3. It's negative 15 and 2/3. So it has the negative, but an integer has to be nice, like just negative 15. So it's not an integer, but it is rational and it is real. If it's rational, it can't be irrational. Okay? The diagram shows how those are separate, right? Irrational or rational. You can't be both of those. All right, 1.48. Not natural, not whole, not an integer. It's not nice enough for that. It is rational. It is real. It's not irrational. Square root of 7, if you did on your calculator, would fill up the whole screen. It's actually an irrational number. Okay? It's not natural. It's not whole. It's not an integer. It's not rational. But it is real. Okay? Irrational is still real. Okay? 0 is not natural. It's a whole number, though. And if it's a whole number, it's an integer, it's rational, and it's real. If it's rational, it can't be irrational. And then this 0.5 has a bar on it, so it's 0.5 with the 5 repeating. Okay? If that's the case, then you can write it as a fraction. That's actually 5/9. We're just not taking time to learn how to do that. If it's rational, it's real. Okay? And if it's rational, it can't be irrational. But it's not nice enough to be natural or whole or an integer. Okay?